Today, we're going to explore one of the most fundamental concepts in chemistry and physics: density. Density helps us understand why some things float while others sink, why certain materials feel heavier than others, and how scientists identify substances based on their physical properties. Density is essentially a measure of how much matter is packed into a given space. Every substance, whether it's a solid, liquid, or gas, has its own characteristic density. We express density using a simple relationship. Density equals mass over volume. Mass tells us how much matter a substance contains, and volume tells us how much space it takes up. When you divide these two, you get a value that describes how tightly the particles are packed. For example, if you hold a piece of lead and a piece of wood of the same size, the lead feels heavier. That's because lead has a much higher density. Its particles are more tightly packed. The same idea explains why oil floats on water. Oil is less dense than water. Density isn't just an interesting idea. It plays an important role in everyday life and scientific applications. Engineers use density to design ships that stay afloat. Geologists use it to identify minerals. Chemists use it to determine the concentration or purity of substances. And even in cooking, density affects whether ingredients sink, float, or mix evenly. As we move forward, we'll learn how to calculate density, interpret density values, and apply this concept to real-world situations. Understanding density will give you a deeper appreciation for the materials around you and why they behave the way they do. Density is defined as the mass per unit volume of a substance. In other words, it tells us how much matter is packed into a certain amount of space. The formula for density is D equals m over V, where D is density, m is mass, and V is volume. This relationship shows that density depends on both the mass and the volume of a sample. To illustrate this, let's look at the density of water. The density of liquid water is 1.00 kilograms per liter. Because 1 kilogram is 1,000 grams, and 1 liter is 1,000 milliliters, we can convert it to 1.00 grams per milliliter. So the density of water is also 1.00 grams per milliliter, which is a commonly used unit in chemistry. One important feature of density is that it does not depend on the size of the sample. Whether you have a small amount of a substance or a large amount, the density remains the same, as long as temperature and pressure are constant. If we have 1 liter of water, it has a mass of 1.00 kilograms. If we have 2 liters of water, its mass becomes 2.00 kilograms. Notice that as the volume doubles, the mass also doubles, but the density does not change. It stays 1.00 kilograms per liter because the ratio of mass to volume remains the same. Now let's compare this to iron, which has a much higher density, 7.80 kilograms per liter. This means iron is 7.8 times denser than water. If you have a 1 decimeter cubed block of iron, it has a mass of 7.80 kilograms. Then, how much mass does a 3 decimeter cubed iron block become? Since the volume of the iron block is tripled, the mass should also be tripled, which is 23.40 kilograms. Even though the mass changes with the size of the block, the density of iron stays constant to 7.80 kilograms per cubic decimeter. Density is therefore independent of sample size, meaning it stays the same no matter how much substance you have. On the contrary, both mass and volume are dependent on sample size. This leads us to an important distinction in physical properties. The properties of substances that do not depend on sample size are called intensive properties. Examples of intensive properties are density, concentration, temperature, pressure, and speed. The properties of substances that depend on sample size are called extensive properties. Examples of extensive properties are mass, volume, length, and time. Now that we understand what density is, let's take the next step and learn how to use density as a conversion factor in problem solving. Density doesn't just describe how much mass is packed into a certain volume. It also allows us to convert between mass and volume in a very systematic way. This makes density extremely useful in chemistry, physics, and many applied sciences. Remember that density is defined as mass over volume. Because density relates mass and volume, we can rearrange this formula depending on what we need to find. If we want volume, volume can be written as mass over density. If we want mass, mass can be written as mass times volume. Density can be used as a conversion factor in dimensional analysis. The conversion factor can be these two forms. Mass over volume is used to convert volume to mass, and volume over mass is used to convert mass to volume. Let's try some practice problems. In the first example, a student places an empty 50 milliliter beaker on a balance and zeroes the scale. After adding liquid, the balance reads 1.385 grams. We're told the liquid has a density of 1.15 grams per milliliter, and our job is to find the volume of the liquid. Since we need volume, we can use a modified equation, volume equals mass over density. Plug the given mass and density of the liquid, unit grams are cancelled, and we have 1.20 milliliters. Alternatively, we can treat density as a conversion factor like this. The given unit, gram, is cancelled. Both approaches give the same result. This shows how density allows us to convert a measured mass into a corresponding volume. In the second problem, a researcher synthesizes a new compound and measures its mass, 0.237 grams, and its volume, 1.789 milliliters. To find density, we use the basic formula, density equals mass over volume. Plug the given mass and volume of the compound. We have 0.1325 grams per milliliter. In a final problem, the researcher accidentally loses 0.095 grams of the compound from question 2. We want the volume lost and then the remaining volume. Since density is 0.1325 grams per milliliter, we can use this to convert mass to volume. Then the volume lost is 0.7170 milliliters. Now, we subtract this from the original volume. The volume of the compound remained is 1.789 milliliters minus 0.7170 milliliters, which is 1.072 milliliters. So after the loss, the researcher has 1.072 milliliters of the compound left. Since we've explored what density is and how to use it as a conversion factor, let's look more closely at how the density of different substances compares. Density varies widely from one material to another, and understanding these differences helps explain everyday phenomena, why some objects float, why others sink, and why certain materials feel heavier than others even when the size looks similar. The table on the slide lists several common substances along with their densities in kilograms per liter. Remember, density equals mass per unit volume. So, when substances have the same volume, the one with the higher density will have the greater mass and thus feel heavier. Let's look at some examples from the table. Ethyl alcohol has a density of 0.79 kilograms per liter, which is less than that of water. Ice has a density of 0.917 kilograms per liter, also less than water. This explains why ice floats. Water itself has a density of 1.0 kilograms per liter. Aluminum, iron, lead, mercury, and especially gold have much higher densities, meaning they are significantly heavier for the same volume. Let's try some practice problems. If all the listed substances have the same volume, which one would be the lightest? We look for the lowest density in the table. That value is 0.79 kilograms per liter, which corresponds to ethyl alcohol. So ethyl alcohol would have the smallest mass and therefore be the lightest. Now, which one would be the heaviest for the same volume? We look for the highest density, which is 19.3 kilograms per liter, the density of gold. Gold is extremely dense, which is why even a small chunk feels very heavy. This comparison highlights how density directly influences how heavy or light a material feels when the volume is kept constant. Next, let's think about what happens when an object is placed in a fluid, like placing wood, ice, or metal into water. The key idea is if the density of the fluid is greater than or equal to the density of the object, then the object floats. If the density of the fluid is less than the density of the object, then the object sinks. This principle is based on Archimedes' principle, which states that an object immersed in a fluid experiences a buoyant force equal to the weight of the fluid it displaces. A great real-world example is the Dead Sea. The Dead Sea is famous for being so salty that people can easily float in it with very little effort. The extremely high salt content makes the seawater much denser than normal seawater, which dramatically increases its buoyant force. Even people who normally sink in a swimming pool will easily float in the Dead Sea. It demonstrates the principle perfectly. When the density of the fluid increases, floating becomes easier. Now, let's try an online activity to reinforce our understanding of density. Log into the course site on D2L. Click the Content tab at the top. In the left menu, open Lecture Material, then select the module titled 09 Density. Under that module, find Lab 09 Density and download a lab worksheet. Complete it as you walk through the online simulation. Return to D2L and under the same module, open Simulation, Density. In the simulation, select the intro window. In the top right corner, make sure Wood is selected for Object A. Place the wood block in the water. Does it float or sink? Change the mass of the wood block in the top right corner and record the volume of water displaced by the block in the table on the lab worksheet. Remember that the volume of water displaced is the difference between the water level before and after placing the block in the tank. If the block floats, do not release the mouse button. Keep the block submerged. Measure the change in water volume before and after submerging the block. Plot the volume of water displaced versus the mass of the block. Alternatively, you may plot the data in an Excel spreadsheet. In the top right corner, make sure to select aluminum for Object A. Follow the same procedure used for the wood block. Select Mystery Window from the menu at bottom. Click the plus sign to expand the density table. Select Set 1 blocks in the top right corner. Use the balance on the left to measure the mass of each block. Drag each block and place it under the water. If the block floats, do not release the mouse button. Keep the block submerged. Measure the change in water volume before and after submerging the block. This volume change equals the volume of the block. Determine the density of each block by dividing its mass by its volume and identify the material each block is made of. Open the downloaded lab worksheet, follow the step-by-step instructions, and complete the lab worksheet.